And we had a student request for this lecture to be recorded. So we're going to record our discussion of chapter 19, which continues today. The main two reactions in chapter 19 are the Aldol reaction, which also has a condensation component to it. And the other main reaction is the Claisen condensation. They're both on this activity here. And we have what's called a simple aldol at the top left. So we need to know the clues that indicate that we're being asked about a simple aldol. Clue number one. You start with a carbonyl that has an alpha carbon that has H's on it. This could be an aldehyde or a ketone or even an ester. Yes. So what makes it an aldol reaction? What makes it an aldol reaction is not the reactant here, but the nucleophile you make. I'm sorry, I take that back. Not the reactant here, but the reactant that gets attacked by the nucleophile you make. Whoa, okay, slow down. If you attack an aldehyde or a ketone, then you have an aldol reaction. And the aldehyde or ketone becomes an alcohol. There's your aldol. Okay, if you attack an ester with an enolate, then you're talking about a Claisen condensation, and you attack the ester and get a ketone when you're done. I'll remind you of these as they come up. So we start with an aldehyde here, and another clue that this is an aldol is that in one box, I treat it with KOH. It can be aqueous or not, that doesn't matter, but you have a base. And then a big clue, the next one looks almost exactly the same, except we add heat. This is a clue that this will be the condensation step right here where you lose the water. And the synthesis, aldol reaction synthesis step is in here. And it's a simple aldol because there's only one reactant. The molecule is going to grow in size. So what are the steps to predicting aldol products? Quite simple. Pick the thing that's about to lose its alpha H and copy it down. When it's stick figures, you don't have to worry about taking this H off. I'll show you this H, but you don't draw H's in stick figures anyway. That H is going to disappear. Going to become an anion on the alpha carbon. And what do we call anions on the alpha carbon? It's the title of chapter 19. They're called enolates. That's the nucleophile. So an anion here will attack one of these unreacted molecules and make a sigma bond to the unreacted aldehyde, which becomes an alcohol. And then make sure you have the rest. CH2C with a methyl and an ethyl. So aldol product predictions are quite simple. You copy the first aldehyde or ketone, in this case an aldehyde. You're going to make a bond from the alpha position to the carbonyl of another aldehyde or ketone. And the carbonyl of the other aldehyde becomes an alcohol because it got attacked and the pi bond broke. And then what happens in the condensation step, this is where you lose the water. Not worth points, but good to keep track. You're going to lose the green OH and another alpha hydrogen. From the same position you stole the alpha hydrogen previously. You end up with a pi bond between the alpha and beta positions. Alpha and beta positions. And sterics says carbonyls are less hindered. So you put your larger group towards the carbonyl. And I am making a mockery of my boxes, which is okay. You can do that on tests too. My box didn't fit my answer. So you want the group that's bulky, which in this case is a carbon compared to a hydrogen, the bulky one to be on the side where the carbonyl is, because sp2 carbons are not bulky, they're flat. So that is the story for a simple aldol. Simple aldol reaction and simple aldol condensation. And that makes molecule A. Let's talk about molecule B, because it looks like they're coming together here. We better know what they look like. So over here, I started with an aldehyde, but I had to do a couple things to it to make it into an ester. And ester is a more oxidized version of the carbon, which gives us a hint what has to happen first. We have 2 bonds to O here. We need 3 bonds. That's oxidation. And we got to go all the way to a carboxylic acid because we do not know how to oxidize to an ester. But we've been oxidizing to acid since chapter 10 in the other course. CrO3 is a favorite. H2SO4. Don't forget, water is essential in the mechanism and in the manufacture of chromic acid, which I guess is part of the mechanism. So you need the water. Now you've got a carboxylic acid and you need a carboxylic ester. It is time for your classic Fischer esterification, which is definitely also on your test. And H2SO4. Typically, you require heat. I won't really grade that heat. If you forget it, that's not a big deal. And then we have the conditions that are a dead giveaway for a Claisen, a simple Claisen condensation. Simple Claisen condensation. What are the conditions? Well, an ester. You start with an ester, but more importantly, to be a Claisen condensation, you have to attack an ester. So both reactions, Aldol and Claisen, all depend on what gets attacked, not necessarily the attacker, which is an enolate, all chapter. When we have one molecule here and you have this, another giveaway, this leaving group matches the base that will make your enolate. That is a dead giveaway for a simple Claisen condensation. The leaving group here matches the base. And you'll look at other videos and I explain why, and I'll just give you a rundown. It's to avoid transesterification, which is a competing reaction. Going from one ester to a different one. We don't want that. Clearly, I want to keep this ester. So I make sure I choose a base that will create the same ester if it does a transesterification, which is not a transesterification if it's the same one. A lot of talk. Predicting Claisens, you start off the same as predicting aldols. You copy the original molecule, missing an alpha H, which means you're going to make a bond from the alpha position again. It attacks a second molecule that did not react with the base, and it attacks it at the carbonyl. But this time, you're not going to get an OH up here like you did over here. No OH, because the O minus comes back and kicks off the leaving group. And if you think about it, the leaving group, OET minus, matches the base you use to make the anion. So OET minus is not only a base here, but it's a catalyst. Yes. And it attacks the carbonyl, and the electrons come back on the carbonyl this time to kick off the leaving group. So yeah. So what kind of products do you make in simple Claisens? You make beta keto esters during simple Claisen condensations. And the simple aldol reaction, you make a beta hydroxy aldehyde or ketone. And in the condensation, you make an alpha beta unsaturated aldehyde or ketone. In our cases here, the blue is an aldehyde. We'd have the same result if we started with a ketone, but we'd end with a ketone. Going along well so far. Now it's time to bring together the fruits of our labor. We made molecule A and molecule B. It'll highlight action on molecule A and B so you can keep track. Molecule A, molecule B. There we go. Now, the cool thing about molecule B, absolute coolest thing about molecule B, is that we have an alpha H that's alpha to 2 carbonyls. Oh my. We know if it's alpha to 1 carbonyl, its pKa is in the 20s. Aldehydes, ketones, it is 20. If it's an ester, like in this simple Claisen here, where we took the H off, the pKa was 25. I don't believe we mentioned that until now. 25 alpha to esters, it's new. Means you add it to your list. Alpha to ester. When we were alpha to aldehyde or ketone, this is review, pKa was 20. And you'll look around at videos of mine and it'll explain why. You'll listen to and read about competitive interference of resonance here. The lone pair on the OET, it competes negatively against the anion that you're about to make. You want to watch a video on that. Okay. So we're going to bring together molecule A, B, and molecule A, and I never finished saying what the coolest thing about the molecule B was. I started and I didn't finish. You guys might even be getting used to that by now. Special pKa, 10. That's new. Give it a color, huh? Green. Also new. Alpha to 2 carbonyls. Alpha to 2 carbonyls. Yeah. I think our list of things that have a pKa of 10 is growing quite large. We had ammoniums from the first second test of Orgo 1. Then on our fourth exam, we had a special kind of alcohol called a phenol, also pKa 10. Yeah. Thiols, that's the SH version of an alcohol, 10. Now we're seeing a new one here, alpha to 2 carbonyls, also 10. We like 10. So you're going to take that alpha H off. I'm going to copy this whole molecule here, down here, missing this alpha H. And I'm going to do it all in blue. And I'm going to try to make room to make a bond to that alpha position. So I can do a little short form down here to CO2 ET. That covers this whole unit here. I'm going to show my ketone. Wait a minute, do I have all the bonds there? CO2 ET is attached to a C. Yeah, I was wondering why things were a little fishy. I don't like it. I lost a carbon. That's why I'm not happy. Apologize. CO2 ET comes to a carbon that goes to a carbon that has a methyl and an ethyl. There. We're going to make a bond after we show the ketone. Once again, I need a little room on the alpha position to make a bond. Laughing at my boxes again. There's a new bond that you're going to make. And it's going to attack something in molecule A. You definitely want to look at the video, which we're not going to do today. But you need to look at it. It says when you have an alpha beta unsaturated aldehyde or ketone, and you have this is going to be an anion here before it makes this bond. It's an anion. And it's a pretty stable anion. Do you know how I know that? It's based on some new information I gave you. The pKa of its conjugate acid was 10, which means it's not that hard to take that H off. We did it with NaOET here. And it's not only a good nucleophile, the C- I made here, but it's also a good leaving group, which means you now have made this a reversible attacking agent. Reversible equilibrium. Most of our other C- we've seen until now, like Grignards, organolithiums, acetylides, they don't add reversibly. They attack, they make that bond and say, I'm here, I'm not going back to where I was before. I was a nasty mother before. I don't like being like that, okay? They won't leave. It'll attack, but it can't leave. This C- doesn't mind leaving. So most of the time, it's going to attack the aldehyde, like we would normally predict from what we knew before. You got a C-, it loves carbon that's slightly positive. But you also have an option of attacking the beta position and having the pi electrons resonate all the way towards the O. And when you watch that video, you'll see the result of that attack is a more stable product. And we know equilibrium loves more stable products. That's what equilibrium's all about. So when you're given a choice of attacking the carbonyl, in the video, you'll see that's now called a 1-2 attack because the electrons attack carbon 1 and they flow to the O-. That's atom number 2. And you have a choice of that or a 1-4 attack where you attack this beta position and resonate all the way to here, the O, which is counting here from where you got attacked as number 1. Electrons flowing up to 4. It's called a 1,4 attack. And it leads to a more stable product. You can only do that if your nucleophile is also a good leaving group. Once again, I'm just trying to verbally cover what's in a video that you need to see, because I can tell this is kind of glazed over look here, which is what I expected. But I want you to watch that video, because I spent a lot of time making it. It's about kinetic versus thermodynamic control. You'll see these words. All I'm trying to say is this particular reaction is under thermodynamic control, and you want to attack that beta position. So I'll make molecule A into a black species. It got attacked on its beta position. Oh, the beta's here. Sorry. And I got to make sure I have the right number of carbons. Beta goes to CH2, goes to C with methyl ethyl. Beta goes to CH2, goes to C with methyl ethyl. Good. What else did the beta have on it? Beta had the alpha on it. The alpha. And I'm going to write down what you get. The alpha is here. And it goes to a carbonyl that's now an O minus. Yeah. Let's see what I got here. I got to put some letters down, or else I get confused myself. There's the alpha. And that had a carbonyl. Something's fishy here. I'm going to get that and that. I think I have everything. Is that right? Let's count all the carbons in a row. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I got it. That's an intermediate. It's an enolate. Enolate. I'll do the mechanism just by, you follow my mouse. The nucleophile used to be this C minus. This C minus. Attacked, the pi broke, making this new pi. This pi broke, making an O minus. This is an enolate in the presence of something with a pKa close to 17, ethanol, the solvent. Enolates are the conjugate bases of aldehydes and ketones, pKa 20. Acid-base chemistry says 17 goes to 20 every day of the week. This intermediate will not stay like this. It will resonate back. Okay? Something's fishy though. The double bond's in the wrong spot. It's up, it should be up here. My goodness. Knew something was fishy. It wasn't an enolate, I lied. I didn't mean to. That's an enolate. And let's follow the arrows that I said and make sure that this is the result, not what I drew before. Where's the pi bond going to be if a nucleophile, and I'll just do it in yellow, nucleophile attacks here, new, resonate, resonate. There's your yellow pi right there. From alpha, I think my alpha beta labels are messed up. Something's not sitting right with me here, ladies and gentlemen. Tell me what I'm doing wrong. I think I figured it out. Attack here, you got this funky group there. What else do you have? You have the alpha position, which has another funky group on it. There's the intermediate. Gotta listen to myself better. And then the beta was here. The alpha's here. Alpha is one away from what used to be a carbonyl. Alpha also has it's a sec butyl group. It's not funky. Once again, this is an intermediate. It's an enolate. Enolates don't stay enolates. Not in the presence of a base, sorry, an acid with a pKa 17-ish. So your final result, resonate the O- into the pi and pick up a new proton from methanol. Here's the proton from methanol right there. And you got your carbonyl back. And it looks darn intimidating is what it looks like. But let's make sense of it. We got everything we need on the screen. You're using this to become a nucleophile. This was molecule B. I treated it with NaOET. That H came off. You made a C-. Given a choice, it will attack this beta position. It says nucleophile here. It's illegible. So some faint color. Nu. There we go. Not now, nu. This C- is the nu. It attacks. So you get a new bond on beta. There it is. It's red. Old pi bond broke and became a pi bond between alpha and the carbonyl. It was a pi bond right there. We had an intermediate drawn earlier. It resonates back and you get your carbonyl. And you made this lovely species right here. There's a lot going on there, guys. All right. Oof. That's all I got. Then we'll move to the bottom. On the bottom, we're going to do directed reactions. This one I know is a directed aldol condensation. I'll tell you why shortly. And this one is a directed Claisen condensation. And the secret is looking at the products. And we're going to go to the top of our screen where we had some clues. What's the product of any aldol condensation? An alpha beta unsaturated aldehyde or a ketone. Oh, look at this. Look at this. Alpha beta unsaturated ketone. Yes. It's a clue you're doing an aldol condensation. When we have, let's see, the original ketone was here. There's the alpha beta. There's a beta ketoester. All right. Just these words here. Green, I don't know. Something. Beta ketoester. Okay. Oh, now I'm crossing molecules. I don't know. Try to delineate some things here. There we go. Beta ketoester here. Right there. Beta ketoester. In this case, not that. Beta keto ketone. Why ketone and not an ester? Good question. Why ketone, not ester? Answer. Nu was and ketone. And ketone. That's not good English. a ketone. Usually we don't start a Claisen with a ketone, but you can. That's what I'm trying to say. It's what gets attacked that's important. And we attacked an ester. How do you know you attacked an ester? Because the new bond is right here, and it's to a carbonyl. It's not to an alcohol. It's not got a double bond between alpha and beta. Those are the aldol things. All right, so how do we do directed aldols? We can't do a simple aldol. I'll just put a note here. If it was a simple aldol, it'd be a great test question. Simple aldol. We're going to do, you got to use NaOH and heat. And you get, hey, more practice. That's what you get. Copy the original. We're going all the way to the condensation here. So here's the original. It's blue. It's blue. The green piece looks just like the blue piece, except the carbonyl on the green that used to be a carbonyl is a C-double-C to the alpha carbon. The green piece, the thing that got attacked, ends up C-double-C to the alpha carbon. Make sure you copy your molecule properly. And you get a C-double-C to the alpha carbon. What's this carbon? It used to be this carbon of molecule, sorry, this carbon of molecule number 2. Copy it with an alpha ethyl. And it looks terrible, but that's it. And clearly, I'm not making that. See, they're not the same. It's a directed aldol. What I have to do is take the alpha H that I want to take off and don't let equilibrium happen. That equilibrium word again. If equilibrium happens, then this thing's surrounded by, sorry, this anion right here is surrounded by this molecule and it will attack itself. I got to make sure I take this H off 100%. That way there's no ketones lying around waiting to be attacked. So I need a much stronger base, one that quantitatively takes this H off. I await 3 suggestions from you for what kind of base I should use to make sure I take 100% of this off. And let me just tell you, I need a pKeq of more than -5. Because that makes it pretty quantitative. And 100% finished reaction if it's a negative. So what kind of base? What's the strongest base you can think of? Just give it to me. Uh-oh. We got nothing. We got crickets, everybody. Oh, guys, chapter 4. Our worst base was like something like sulfate or chloride or perchlorate. Those are the worst bases. I need the best base, strongest base. I just told you the worst ones were the conjugate bases of the strong acids. What base would give the strongest base? The conjugate base of which acid? The weakest. Give me a base, the conjugate base of the weakest acid. Nobody. It's Monday, obviously. Nobody? I await an answer. Coffee break. Thank you. I need the conjugate base of the weakest acid you can think of. Just tell me what to write. Step 1. KH, that's the 4th strongest acid that you weakest acid, H2. You gave me the 4th strongest base. H minus is what he said. He said KH. I didn't hear the K. I heard H minus. I want the conjugate base of the weakest acid that you know of. There's an acid with a pKa of 50. The conjugate base of an alkane. If the answer, before I even had my sip of coffee. There we go. All right. The problem with that is, great answer, by the way. Say you took a butyl minus, like butyl lithium is a butyl minus, right? Well, we know what butyl minus likes to do instead. We did that on our last test. It attacks the carbonyl. It likes doing that better. Oops. Next strongest base, conjugate base of an alkene. You get the same problem. And conjugate base of an amine. Now you're gonna get competing imine formation, but we're getting closer. We're getting closer. We're going to use the conjugate base of an amine, which would be an N minus, but I need it to avoid attacking the carbonyl. I need it to have bulky groups on it. And this base is huge on our test. Huge. We're going to use it lots of times. And here it is. Put it down here. Bulky. Careful the spelling of this. You might think it's the functional group amide. It's not. Base avoids competing imine formation. N minus with two moderately bulky isopropyl groups and a lithium cation spectator. Lithium diisopropyl. And here it is. It is not what you learned to be an amide before, so don't say it that way. Lithium diisopropyl amide. I know. We never test pronunciation, but we need a word that says the anion of nitrogen. And we've been doing that from 141. Like, what's the anion of chlorine? Chloride. What's the anion of an amine? Amide. I know, because we can't say amide. It's stolen. It's taken. It's a functional group with a carbonyl in it. Is there a carbonyl in this thing? No. So, just like the word polish, like polishing your furniture, and the word Polish, like you're from Poland, spelled the same way. There are definitely different meanings, right? English has many of those, and amide is one of them. And its short form is LDA. That's how popular it is. And it loves doing one thing. Loves grabbing the least hindered alpha H. That's what LDA does. So when you have choices of alpha H's, you're going to go for the one on the less substituted carbon, because that's less hindered. Okay, so back to our discussion. Wow, this is a big segment, huh? So we're going to use LDA. And we have to be careful. I got to make sure I take that least hindered H and there's no ketones left over. Okay? Because the LDA has a choice of this H right here up top or the H that's here. And based on what I said about LDA loving to do something, it's going to like taking the top one. So I want to take that top one off, and I want to take it 100% off. So there's no attacking a carbonyl with this C minus you just made, because there's no carbonyl anymore that doesn't have a C minus alpha to it. Now you've got to add the aldehyde or ketone that would give this result. And it's not a ketone because this carbon here has an H on it. It was an aldehyde. Step 2. And I'm about to apologize because in this one, a step 3 is actually necessary. And I didn't indicate it. Sorry about that. So you're at the aldol reaction product, but there's an O- up there. The green O became an O-. Picture it now in your mind. C- from step 1 is an enolate. It attacks this carbonyl and makes an O- in step 2. I need one O- to become OH. You know how to do that. HCl. And then I'm going to add heat to do the condensation step. So you're going to lose the OH and another alpha H to make the aldol condensation product. Yes, we're making an aldol condensation product. We established that when we looked at an alpha beta unsaturated ketone. So HCl to protonate the O, heat to make the OH leave. Do that mechanism later today. I hope. And then we're going to do a directed Claisen. It's a Claisen because we're going to be attacking an ester that looks like this. Now I got to take it off the H on the the more hindered carbon. I can do it with LDA, although LDA doesn't like going for that H, does it? I'm going to use LDA limiting and tell you a brief story that's more fully discussed in a video. LDA limiting. It just means less than 1 mole of LDA for 1 mole of ketone. It's like 95% instead of 100%. What happens there is your 95% of this reacts, leaving behind 5% ketone unreacted. Now you've got an enolate of a ketone and a ketone. They're going to shuffle protons. The enolate you made is going to take the alpha H that leads to a more stable enolate. You want to watch the video. You've now made this under thermodynamic control by letting equilibrium be established. Instead of 100% reaction like you did here, you've let equilibrium happen. And that favors an enolate on a more substituted carbon. That's the attacker. It's going to attack an ester that looks like these 4 carbons in a row. And here it is. CH3O. 4 carbons in a row. And once again, I apologize. This is also needed 3 steps. You don't need heat on this one. You just need to protonate the alpha position. Right there. Although it doesn't look protonated, does it? Typically, a Claisen is always followed with HCl. So I just want you to learn that. This is the end of a Claisen. Look up here. The end of the Claisen was HCl. In this one, because there's no alpha H there, you really didn't need the HCl, but I want you to just always put HCl as the finishing of a Claisen. Just do it. In this particular example, there's no H to be put there, so you didn't need to put it there. And what's going on here? The big finish here. That's a long video. It's going to be like an hour or 50 minutes. Hey, KOH and heat. We had KOH and heat up here. If I had KOH and heat right here, I'd want you to go straight to the final box. You do have to do the middle box in the mechanism. But if you have heat, it means skip the aldol reaction product and go straight to the aldol condensation product. And you say, okay, how do I do that? Well, you've got to make an alpha H like here. 1, 2, 3, or oh man, or here. There's something about this question that I don't like, and I'm going to just stop it now before I get too carried away. I don't like this question because it doesn't make a ring size that's good. We'll make ring sizes that are good later. So just scribble this one out. It's good. I'll go to the previous one. Just scribble out this whole deal. We'll talk about making intramolecular aldols happen in our next activity anyway. Thought I had one going on here, and it's not a good one. So you got the first page has a blank for you to practice on, and we got this one with a lot of good stuff. I strongly suggest before you watch this video again, you watch the video about thermodynamic versus kinetic control. It'll probably have those words in its title. And then I bid you adieu on this video. And I hope everything worked out nice.